All right. So the first question was to have more information on this upper bound test and why do we need this upper bound test? How do we compute the upper bound test for rate monotonic scheduling? And so let's take these two tasks over here. They have an execution time of one for task one and a period of two. So it's basically executing 1 unit of time every 2 units of time. And task one has a higher priority because its period of two is smaller than the period of task three. So the rate monotonic just means that the faster the rate or the higher the priority of the task. So the task that is most frequent has the highest priority. And that's the arbitrary choice of scheduling these tasks. And so in this case, task two here has an execution time of 1.01. And we see that if task two tries to execute, then it basically misses its deadline of 3 because it finishes one time unit, but then gets preempted by task one. And then cannot finish this 0.01 over here in time because its deadline is 3. So the confusing part really is that if we look at the total utilization of this task, right, that's the ratio of the execution time C1 to P1 plus C2 over P2, it's 83%, 83.3% of this task over here, of the schedule is essentially is being used, and this is unschedulable. Now, if I change task two's period to be 6 and I change task two's execution time to be 2.4, which is more than double. So therefore, the utilization of the processor utilization is zero point 0.9 now. So, our intuition would be like, wait a minute, if it's not schedulable with 0.3, 8.3, 83.3% utilization, then if the utilization goes higher, it's probably not going to be schedulable too. But in this case, it is actually schedulable, right? So where we can see that we can schedule this. And so why did this happen? Intuitively, why this happened was because the period of task two is longer. And even though the utilization, the execution time became more, it has a little bit more time to split up its work and to be able to run the task, you know, even though it is getting preempted. So task two basically got preempted once, then got preempted again, then got preempted the third time, and then then it finished. So the funny part here is that with a lower utilization, the task set was not schedulable. With a higher utilization, the task set is schedulable. So this really is like sort of a little bit, non-intuitive because schedulability depends on the task set. It does not have any relationship between utilization as much, right? So there's no clean relationship. There is some relationship with utilization. And what we want is if we ran like these tests for many task sets, right? So where I had these two tasks and I changed the periods and I changed the execution times for each of them, and they had different utilizations. So here I had some tasks that had some pretty moderately high utilization was unschedulable. Lower utilization is schedulable, right? And in this case, I have a task that has a really high utilization and it's schedulable. Here's another one with pretty close amount of utilization, but it's not schedulable. So it's not clear which ones are schedulable, why some are schedulable, why some are not schedulable. And because this is really like a combinatorial problem of, is there enough breathing time for lower priority tasks to get scheduled, even though they're going to get preempted by higher priority tasks? And so back in 1973, there was a seminal paper by Liu and Leyland, who were two authors who looked at this problem. Even before like computers and operating systems were mainstream, 1973 is a really long time ago, right? Way before even I was born. So, and they started to look at this kind of problem. They were like really way ahead of their time, and they didn't have like GPUs and supercomputers to compute this out. If you gave this problem to somebody today, they would say, "Oh, let me just run lots of simulations." but if you run lots of simulations, you can't get some theory out of it. So what they were trying to look for is what is the least upper bound. So where below this utilization bound, all tasks are definitely schedulable, right? So above this bound, we are not sure. They may or may not be schedulable. Deadlines may or may not be missed. But definitely under this utilization bound, all deadlines are met, right? So they found that out by looking at this combinatorial problem, and so we wanted another way to ask this question of finding what is this least upper bound is that what is the lowest utilization for an unschedulable task set, right? So if I want to find that unschedulable task set, how low can you go? And then that's the bound over there. Or another way is to say, well, so I'm really trying to have a bound for something negative like that, right? So it's unschedulable, and that's the lowest utilization it's had. So um, and we also sort of say what is the lowest utilization of a critically schedulable task set over here. And by critically schedulable, it just means that at the start of, time over here, which is at time 0, both the tasks are backlogged. Both the tasks are ready to run. Both the tasks have jobs waiting to be executed by the processor. The processor is fully busy. In fact, you can see that the processor is busy, then busy, then busy, then busy, then busy, then busy. No spring break yet for this processor. And the processor only gets a break after this point. So this whole time from 0 till 5.4 over here is called a busy period. The critical instance is at 0 where all the tasks are backlogged, right? So these are uh, kind of definitions, right? Critical instance is the time where all the tasks are backlogged and there is the maximum workload requested of the processor. And once the processor starts to execute that workload, it basically begins a busy period. And that just keeps the processor busy till the work is done. And then the work again starts after 6 over here, like that, right? So, and then after 6, this pattern will keep repeating. And then that's all. So the formula that they found, and if we had a longer course, we would actually go through the, the formula over here and the derivation, but the formula that they found is over here, right? So but they look at so for each task, we calculate the utilization, which is the ratio of the execution time and the period. And we get the utilization of the task set. And that is the total CPU utilization. If the utilization is over 100% or over 1, then it's definitely not schedulable. If the utilization is less than 1, then we need to see what is there, right? So now they figured out that if the utilization is less than what they find as a utilization bound based on this formula of n multiplied by 2 to the power of 1 over n minus 1, where n is a number of tasks. So it actually does not depend on what's the execution time and the period of each task. It's just saying for the number of tasks, for one task, you can get 100% utilization. Okay, that makes sense. For 2 tasks, the least upper bound of the utilization is 82.8% of the processor. So if you basically have a utilization of your task set that is less than or equal to 0.828, then the task is definitely schedulable. If it is greater than 0.828, then it's inconclusive. We don't know if it's schedulable or not. And therefore you can just plug in now in this formula and say, well, my task set has some utilization and I have 5 tasks. So therefore your utilization bound is 0.743. And if your total utilization actually of your task set is less than or equal to this value, then it's schedulable. And and if you make this, extrapolate this to a large number of tasks, it basically saturates, and it saturates to 0.69 or 69% of the processor's total utilization, right? So you give me like 1 gigahertz processor, and I can only utilize, in my pessimistic case, I can only guarantee that these tasks with this upper bound test, up to 69% of utilization, the task will be schedulable. After that, I'm not sure. And so that's just the part 1 of this lecture, that was looking at this utilization bound test. And so here's an example. If I have an execution time of 20, period of 100, and so on, and my total utilization is zero point 0.2 plus 0.267 plus 0.286, which is 0.753. That is less than, if I plug in my utilization bound for 3 tasks, 0.779. So this task set is definitely schedulable over here, right? So now what about the remaining CPU capacity? That is 24.7% of the CPU that is still remaining. That can be used for any background tasks that don't have a priority, that like say backing up to Google Drive or to Dropbox, or just downloading your torrents in the background, and so on, right? So that's the upper bound test, and then there are some more examples for the upper bound test and how you apply that. And uh, and and then the problem now is that, well, what do you do if you do not have, if you have a utilization that is greater than this value, right? So if I change this utilization, which was originally 0.69, which is less than 0.773 for 3 tasks, and I changed, that's for this task set, right? So I have another task set. I'll go through the second example, and this task set over here has a total utilization of 0.69, and that's less than the least upper bound limit by plugging in 3, and so I'm fine. But what if I make task three's execution time 3? So I change it from 1 to 3 over here. Then the utilization of my 3 tasks is 0.89. And then I need to figure out, well, look, 0.89 is greater than this utilization bound. So the utilization bound test, upper bound test, does not provide me any information now. It just says it's inconclusive, may or may not be schedulable. This test is only a sufficient test. It's not a necessary condition, right? So if you want to have like a if and only if proof, then you need to be sufficient and necessary conditions need to be satisfied. In this test, it only has a sufficient test. That means it's not necessary that this condition be satisfied for the task to be schedulable. So what you would do now in this case is, well, you would just draw the timeline out, and then you would see, is it schedulable? And the easiest way to draw the timeline is task 1, ignore all the other tasks, just draw task 1, because task 1 is always scheduled first. It does not care about any other tasks. It'll just bump all the other tasks or preempt them all whenever it comes into getting scheduled. And here's the start of the task, the deadline for the task, the next deadline for the task, and so on. And then for task 2, we don't have to care about lower priority tasks. We only have to worry about higher priority tasks. After higher priority tasks have executed, then task 2 can execute, and then we keep switching back over here, right? So this pattern, now you can see this pattern looks like it's even, and it's kind of like a set pattern, but that pattern may not be repeating in the same way, right? And so what would be, like, when would this task set repeat like that, right? So if we have now periods of 4, 6, and 10, and this task set, till when do I have to run this till when do I have to run this this task set over here, and draw this out to make sure that I know it's schedulable for this task set, right? So
Is it just like the hyper period or like the least common multiple of 4, 6?
yeah, and what is that over here?
Um, it's no.
What's the lowest common multiple of 4, 6, and 10?
Is it 60? I feel like it should be smaller than that, actually.
What is smaller than that? Yeah, so we'll go with 60. And so basically now you have to draw this out till 60, and you're like, man, this is just tedious. And that's when we go and look at the second test, right? Which is basically the response time test, which we went over on Tuesday. So I'll go through the next question was there. So that the first question was, what happened to this? Okay, so I'll go through the so before we switch to the next question. So some other folks joined in. So why don't you say hi, put your videos on, and then you can ask a question, and I'll add that to the list of questions that we'll go through. Okay, I think Peter joined in, and Luyu joined in. So any questions, guys? You can just unmute.
Yeah, not really.
Okay, no questions. Okay. All right. So the next question, so did that answer the question of the upper bound test?
Yeah, it did. Thank you.
Yeah. Okay. So the second question was, how do we schedule a task that has uh, how do we schedule interrupt tasks, right? So hardware interrupts, they don't necessarily, follow the same rules as other tasks. They basically are special tasks, right? So how do we do that, right? So we'll go through in the latter part of this lecture. Yeah, so this is scheduling with interrupts. And so let me know if you can see my screen. You can see my screen? Okay, great. So interrupts are basically not regular tasks, right? Because regular tasks that in our case over here, we assume that they are periodic tasks. That means they have a period, they come in on time, they execute, and then they leave. They basically finish their work, and then they only come back when their next admission time is there, right? So it's kind of like our weekly lectures, right? Our weekly lectures are only on Tuesday and Thursday, and we start at 12 o'clock, we finish at 1:20, and then that's it. There's no more lecture beyond that. And but an interrupt is kind of like, oh well, we have this COVID virus now, and now we need to have like a special lecture. I remember when I was in high school, my chemistry teacher, he would go way beyond the syllabus and teach us like college grade chemistry, to as if we were all going to become PhDs in chemistry. And he would have special lectures every Saturday. So that was like an interrupt, but in that case it was kind of a periodic interrupt. And so with an interrupt, it basically is very inconsistent with rate monotonic scheduling, because the interrupt handler, it comes in at an arbitrary time, and then it is the highest priority task, and it just boots everybody out and says, okay, I need to execute right now. So so it's kind of like you're in a long queue in the in immigration, and then somebody comes in and says, hey, I'm like a US diplomat, and I basically, they can just preempt everyone. Or what's happening in Philly right now, if you look outside Trader Joe's at any time, people are all queued up, and then let's say some hotshot person comes, Mr. Trader Joe's himself, and says, hey, I'm going to shop here, and he says, I'm going to boot everybody off the queue and just go in first, if that would happen, right? So um, yeah, the answer is, don't go to Trader Joe's or Whole Foods. They're just too trendy right now. So the interrupt processing, now if the interrupt comes in, it'll delay all the other tasks, and it'll delay the highest priority task, the next highest priority task. It'll delay, it basically ruins the entire schedule of everything, right? Because it just comes in at some arbitrary time. It has to be the one that executes right away. And so how do we basically now allow interrupts to happen, and allow our formulation of this rate monotonic scheduling to occur, but taking into account this inconsistent sort of semantics of interrupts over here. So, so let's look at an example, right? So we have three tasks, tau 1, tau 2, tau 4, that are regular tasks over here. And then here and they are basically listed in their rank of their periods over here, right? So there's 20, 40, sorry, there's 100, 150, 200, and then 350. And then you're like, wait a minute, tau 3 is an interrupt handler, and that's why we marked it in a different color. But the interrupt handler, it does not really have a period. I mean, it definitely has an execution time to execute the interrupt handler, but uh, but the period is something that we assign it, right? So, or say like this interrupt is kind of the sampling rate or the maximum sampling rate of this interrupt handler. And say like if I have an interrupt to get my IMU reading or some sensor reading, I say I want to sample it at this rate, and but that makes it a periodic task, right? But most interrupts, they don't have like a rate, they just happen when they happen. When a key press happens, a key press happens. So what we do is we assign it some period and say, well, an interrupt can't happen more frequent than this period, and we can rate limit that interrupt. But that limit is not something we are imposing. That's just some limit that was already imposed by the system in terms of a sampling rate or in terms of how frequent this interrupt could happen. And if it happens more frequent than that, then we won't be able to service that interrupt again, right, within a faster period. So we're going to assign this interrupt now some arbitrary period, but actually in this case, the period doesn't matter that much because it's just the execution time. Because when the interrupt comes in, it says, I don't care what my period is or what my priority is in your queue. I'm always the highest priority. So actually this task tau 3 should always be on the top, even, but it's breaking these semantics over here of ranking tasks based on their period, right? So shorter the period, higher the priority, according to rate monotonic scheduling. So if we were to run this task now, we have tau 1, tau 2. If tau 3 happens, well, then tau 1 is not going to happen. And it's not like if we were to just execute tau 3 as a routine task, not as an interrupt, then tau 3 would execute in this way. It would get preempted by tau 1, and then it will finish its job over here, and it will continue. The second time it runs, it doesn't get interrupted by anybody. So you see there's some pattern where sometimes it gets preempted, sometimes it doesn't. But tau 3 is not like any ordinary task over here. We can't treat it as an ordinary task like that, right? When tau 3 comes in, then tau 3, an interrupt happens, it just boots everybody out and says, hey, I am the highest priority task all the time, regardless of whoever else is there in the system. So we say, fine, if tau 3 is the highest priority task, let's just treat tau 3 as, you know, a task that is always going to preempt everybody else. So when we run our computation for, you know, what is the upper bound test or the response time test or calculate the utilization, then we treat tau 3 as the highest priority task. And we say, well, it's not going to happen more frequently than 200 time units. And when it does occur, it consumes 60 time units. And so it has a deadline of 200 time units, right? So so the period over here is just saying that this task won't happen more frequently than that over there. Like our key press can't happen faster than say 50 milliseconds, right? If that's how fast like a really fast gamer can press a key press. So 50 milliseconds is a long time from a computer's perspective, right? Which is running at, you know, hundreds of megahertz or, you know, gigahertz like that. So when we want to calculate what is the effective utilization, we basically say, well, this is our usual utilization, you know, of all the tasks that I have that are essentially, uh, you know, so we're going to get preempted by, you know, by who? We're going to get preempted by tasks that are higher priority than me, and we're going to get preempted by, you know, the interrupt task like that, right? So here I want to calculate, well, what is the execution time of all the higher tasks who have a higher priority, right? Or have a period less than me or less than I over here, right? So we are for the, what is the utilization for task I? We can find that out by saying, well, I'm going to get preempted by all these higher priority tasks. This is my execution time. And then this is the execution time of the interrupt task. So I'm going to always add this execution time of this interrupt task, and that gives me my utilization. And so let's take a look at how that would be, right? So if there are no tasks of with a higher priority, then I just have this interrupt task, and the interrupt task basically will execute as the highest priority task, and that's the and the and we would compare that utilization to just saying if there is only one task in the system, and that's 0.3. And how did we get 0.3? We just divided. Wait 1 second. Yeah, 60 divided by 200 gave us 0.3, and that's less than 100% of the processor, so it's definitely schedulable. Now for task tau1, we have to look at, well, how much tau1 is not getting preempted by any other regular task, but it's definitely getting preempted by this hardware based task, and it has its own utilization, right? So tau1's utilization is 20 over 100, but we also need to add the utilization of this other task, which is the interrupt task. But the interrupt task has a period of 200, but here we assume that, look, in 100 time units I can get interrupted. So in this case, we will make the interrupt task period 100, because we are only looking to a horizon of 100 time units, and within that I definitely can get interrupted. So I will not use 200 as the interrupt tasks period, but just as 100. So here we are actually making the system more conservative, because the interrupt can occur at any time, and if it does occur, then it will definitely preempt me as a higher priority task. So the total utilization then is 80%, and 80% is less than 100%, because I'm just computing this only for one task. The interrupt task is not calculated as part of the number of tasks in the system. It's almost like that is an added extra utilization in the system, but it's not treated as a task then, because we are always adding it as some fixed cost or fixed utilization that is sort of residual in the system like that, right? So then if you look at tau2, then I have to say, okay, well, tau2 gets preempted by tau1. That's a higher priority task. Tau2 has its own utilization and the utilization of the hardware task. So tau2 can get preempted by task 1. Its execution time is 40 over 150. And then we say, hey, this hardware task now can happen once, definitely in 150, every 150. And so now we basically expand the period for this hardware task to be the largest period of the high priority task that we have so far, up to when it reaches 200. After that, it just stays at 200. So we are making this hardware tasks utilization more conservative, and it's higher than its actual utilization. But now we have a system of two tasks, and we compare, okay, we have our utilization of 0.867, and that's greater than the U2 utilization. And so it's not conclusive whether it's schedulable or not. And so we would have to do a response time test to see that, right? For tau4, similarly, same thing. We look at tau1, tau2, tau3, and tau4. And tau4 is 40 every 350. And in this case, tau3 is basically just treated as, with its actual utilization for its period of 200, right? Because now this will happen at most once every 200 time units, and we are looking at a horizon of 350 time units. So in 350 time units, I'll get preempted once by this task, once by this task, at least once by this task. And this is the total utilization I have for 4 tasks. And this is still greater than the utilization bound from the utilization bound test. And so it's inconclusive if it is schedulable or not. When it's inconclusive, you got to run that response time test, which we went over on Tuesday. Oh, so this is just a way of showing how we incorporate hardware-based interrupts as a special task in calculating what is the total utilization of the system over there. So let me know if that made sense. If you still have more questions regarding that. Okay, and so what was the question regarding EDF? What did you want to know about EDF? Do you want me to just go through the EDF slides?
Yeah. I'm sorry.
Okay, so let's go.
If you could just like get us start on it or something.
Yeah. Okay, so let's look at EDF. So I'll share the screen with EDF. So we'll just look at the basics of EDF. There are actually, this slide deck only has about 16 slides. So I can just go through the whole presentation. And if you have questions, then just let me know. So what is the problem with, fixed priority scheduling? For one, the problem is that we need to figure out what the priorities are before we run the program. And then once that is set, then it's kind of a little rigid. And let's look at how rigid it is. And then we're going to look at like, okay, well, here is a different way of doing things, but which is a lot more flexible than a fixed priority scheduling thing. And the general philosophy of, these are all resource allocation problems. Like, um, a farmer has, some fertilizer and some pesticide, but not enough to cover all the entire area that is being farmed. And they need to figure out how to use the fertilizer and the pesticide in the best way, and where to put it in a targeted manner so they can maximize their yield. So that's like a resource allocation problem, right? So where you have some scarce resource like the fertilizer and the pesticide, and you're trying to figure out how to use that. If the farmer had decided, okay, before the harvest season, the farmer decided that I'm going to use the fertilizer only in this part of the farm and not in any other part. And but then when the season started, the the fertilizer was actually required in some other parts of the farm. Then the farmer has to say, well, this fixed allocation of resources is usually never, very efficient. We need to know the context of the system. We need to know what's happening during the runtime of the system to make more adaptive resource allocation decisions as we go through. And that's what this earliest deadline first is going to do. It's an example of a dynamic priority scheduling algorithm. And so in fixed priority scheduling algorithms, they are basically just deciding what the priorities are at compile time or at design time. And then they are fixed for the life of the task, right? With dynamic priority scheduling, the priority of the job, like so for rate monotonic scheduling, the priority of that job is inversely proportional to the period of the task, right? So it's monotonic with the rate of the task. And but now with dynamic priority, the priority of the job is inversely proportional to the deadline of the task, right? So what is the deadline from now? So, and that's how we normally work, right? You have a homework that is due on Friday and another one that's due on Monday. Which one will you do first, right? Normally we would do the one that's due first, right? So there's a saying, right? First things first, but not necessarily in that order. Um, but in this case, we are going to do first things first. What is most urgent? We're going to do that first. I don't really care what your priority is, but so going back to the airline sort of, analogy, if you're waiting in the queue, to get in this TSA queue to get into the boarding gates for the flights, and say like I got to the queue first, but my flight is after 2 hours. It almost never happens. I'm so early. But and let's say now you come in and you say, hey, my flight is going to fly out in 25 minutes. I really need to go. And so if it was first come first serve, I'd be like, sorry, first come first serve, I'm still going to stand at the head of the queue. And then you're going to be like, but that's silly and that's not fair. But then I will argue back and say, but that's fair because we are in a first come first served queue. And then say like the Delta Airlines person comes in and says, oh, well, whoever's flying on Delta Airlines, and their flight is in 25 minutes, please come to the head of the queue. And so they reprioritize the queue and say, we are going to temporarily suspend this first come first serve, uh, which is kind of unfair, but then it prevents people from actually having a big loss of not getting onto the flight. And we're going to allow all these Delta airline passengers to come first to the head of the queue because their flight is next over there, right? And so then I could say, well, so that is basically they're prioritizing the Delta airline passengers based on their relative deadline. And now United Airlines comes and says, hey, because the Delta Airlines people are come to the head of the queue, they're going to delay all the United Airlines passengers from boarding, and that's not fair. So let's put all the United Airlines passengers right after the Delta Airlines passengers, and then this would be the way that many libertarians would want the world to be, that every company can pay to prioritize their passengers, or they can ask their passengers to pay them to prioritize them, which is essentially like TSA pre-check, right? So I pay $95, and then for 5 years I can always go to the head of the queue. So now there are some problems with this, right? So with first come first serve, we see the problem. The problem is that just because the order in which you arrived at the queue doesn't mean your urgency, and does not mean what your your importance is, right? Your semantic importance, if you're a diplomat or if you're some big shot like that, right? Then comes, so that's where this earliest deadline first comes in and says, look, let's just serve the task. The highest priority of a job is one which has the earliest deadline. It's just that simple, right? And that's it. So let's look at an example, right? So if we schedule some tasks, say in this 142638, this is just the execution time period of the task. And so here this task basically has a utilization that's greater than the response time bound over here, and the deadline is a miss with rate monotonic scheduling. But let's look at what is happening with this task, right? So highest priority task comes in and says, I'm going to execute one time unit every 4. So it actually has some room where it is not going to be executing. It has basically 3 time units where it does not have to execute until it misses its deadline. But no, whenever it comes in, it has to be the first task to execute. Boom, 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 it's done. And now the next priority task has to wait for the highest priority task to execute, and then it can go and execute over there. And and then comes the third lowest priority task, and that's like basically you're not a diplomat, you're not TSA pre-check, you're just a regular citizen or regular passenger, civilian passenger, and now you're in the queue, and then you've been waiting in the queue, but then this diplomat comes in, TSA pre-check, 2 people come in, and then you're like waiting, and then one person goes from your queue. Then again, they get interrupted by another diplomat coming in or some military person coming in, and then another person goes through from the regular queue. Then the people from TSA pre-check, a bunch of them come in, and then they preempt, and then by that time, the third passenger in this Tau 3 basically misses their deadline. And this was their deadline over here, like the deadline of 8. And then you can look at this and say, wait a minute, this doesn't make sense, because Tau 3 missed its deadline, but Tau 2 had so much time till its deadline, and Tau 1 had so much time till its deadline. And you're like, what? They are just going into their airport lounges and having like, a gin and tonic, and this guy's having like his what's that, White Claw over there, and they're just chilling out in their in their lounge over there, right? And but then you missed your flight, and like that's not fair, because why can't they just adjust a little bit and make the system happy, right? So So we could have done it like this. I could have said, okay, well, why don't we just schedule everyone based on, so what would we have done over here? We would have just moved, said this task, wait, I need to execute before this deadline. So just move this one away over here. Can I just shift that out and then just execute and finish my job here? I could have, and everyone would have still been happy, right? So this is just saying that, look, something that was not schedulable in rate monotonic scheduling, because of the rigidity of the ordering of the task according to this fixed priority, is causing this task to miss its deadline. But if we have some flexibility by scheduling based on the same task set now, based on the earliest deadline first, then I can actually schedule the task, because I schedule tau 1, then tau 2, because tau 1's deadline is most urgent. So therefore its deadline is first. Then the next most urgent deadline. And basically I'm just trying to look at who's the next most urgent deadline coming up. Then I just say, okay, tau 2 is coming up next. And then I say, okay, now you're next. Then after that, tau 3's deadline is next. And of course, also tau 1's deadline is next. But tau 3 will execute completely and not get preempted by tau 1, because it is the highest priority task. Then tau 1 executes, finishes. Then we look at who's the next deadline. Then next deadline is tau 1 and tau 2. I say, fine, tau 2, you've been waiting, go ahead and execute. And then tau 1 execute. Then who's the next deadline? Tau 3. And so here you can see two things, right? First of all, this task set is the same task set, is fully schedulable, right? And the second thing is that the same task set is schedulable, but it's also that these tasks now have less preemptions by any other higher priority task. They're basically executing almost contiguously without any preemptions. So that's also less overhead when we are executing that, right? So, and then we let this repeat, and we have like 4, 6, and 8. What is the what is the lowest common multiple here? So 24, right? So then we let this run till 24, and then we see, okay, look, it's not going to repeat, and it's going to repeat after this, and everything is schedulable. So great, with earliest deadline first, by making the priority dynamic based on who is the next most, whose deadline is the earliest deadline, that task has the highest priority. We're able to schedule that task, and we are able to actually extract more utilization out of the system and still have a schedulable task set. So the general approach over here is that, with so I won't go through these proofs over here, but what you need to just know is that I can give you the intuition for the proof of how this is proved to be the optimal dynamic scheduling algorithm, right? So what we mean by dynamic scheduling is that we are determining your priority dynamically at runtime based on the urgency. And the urgency is a relative urgency, right? Is your flight flying before my flight? It's not about, am I TSA pre-check or not? So it's a very different way of now providing the priority for these tasks. And so the second part you want to also notice is that, so with rate monotonic scheduling, we had some high utilization and it was not schedulable. But with earliest deadline first, the utilization bound is 100%. If the utilization of the task is less than or equal to 100% of the processor utilization, or less than or equal to 1, then the task is always schedulable. So that's really simple, right? So now, there are other authors that went ahead and proved that earliest deadline first is the optimal dynamic priority scheduling algorithm. And by that, what they mean is that that if there is a set of jobs or or tasks that are schedulable by some algorithm A, then that is a dynamic scheduling algorithm. Then it is also schedulable by earliest deadline first. Basically, it's saying that if you can schedule a task set, then so can I do that with EDF. And so this is a pretty strong and bold statement saying that EDF is the optimal scheduling algorithm for single processors. It's always going to be able to schedule a task set if it is possible to schedule it, right? So how they proved that, I'll just provide the intuition, is that take some arbitrary task set over here. These are just like, these are three different tasks. There's a light blue task, a dark blue task, and a green task. And we are scheduling them over here, and they have different sort of deadlines over here, right? So, so in this case, this has been scheduled according to some scheduling approach, and we don't know what that is. And what I'm going to do is I'm going to go through the sequence of the jobs. The jobs are the instance of the tasks as they're being scheduled during each deadline. And I'm going to basically swap them out to follow EDF. So the first deadline is the green deadline. So then I'm going to swap out when green happens and some other task happens. So in this case, now green is happening after blue. I'm going to swap it because green should happen before blue for this deadline over here. And then I'm going to keep swapping till basically I have an earliest deadline first, that green happens first because its deadline is first, then blue happens after that because its deadline is next, and then dark blue happens after that because deadline is next. And so I can, by doing this iterative swapping over here, I'm taking any arbitrary scheduling algorithm that could schedule these tasks, and I can show that by ordering it with EDF, I can still schedule these tasks and they do not miss their deadline over here. And that's just the graphical way of the proof. If this was like a graduate class, we would actually go and derive the proof over there. And why do you care about deriving these proofs? Because that then you can actually show that these algorithms, can provide guarantees. And why do you care about providing guarantees? Because then automotive companies, satellite companies, rocket companies, aircraft companies, not just companies, but aircraft systems, they all will be like, great, now we want to use this algorithm because there are some proofs and there are some guarantees that the system will always be schedulable. And that's exactly what they want, because that's, if you can guarantee safety and performance, then you have a lot more customers who are working on safety critical, life critical systems over there, right? So what's the advantage of EDF over fixed priority scheduling? The obvious advantage is that EDF can go to a maximum utilization of 100%, and fixed priority scheduling has an average utilization of about 80%. The worst case utilization is 69.9% for a large number of tasks, but on average it's about 80% processor utilization. We don't need to define priorities. EDF has less context swaps, and EDF is basically the optimal, scheduling algorithm. And there's less idle time, between execution of tasks. So now you might say, okay, well, but if you look in the world, EDF is almost never used in the real world. Rate monotonic scheduling is used in the real world, but EDF is not used in the real world because it has two basic negatives, right? So one negative is just, okay, well, it's because, you have to compute this online, and there's a lot of overhead in computing whose deadline is next, right? If we have the RTOS lab and we're able to run the RTOS lab, then you would actually have to take operating system that has fixed priority scheduling and convert that to EDF scheduling. And that's part of the RTOS lab that would have gone out if we were on campus. But the biggest disadvantage of EDF is that when you have an overload, then, an overload is when you basically cannot facilitate all tasks. So then all the tasks start failing over here with EDF, because we're trying to meet a deadline, but you miss that deadline. But in trying to meet that deadline, you basically use up the time, and then the next task can't meet the deadline, and then the next task can't meet the deadline, and it basically cascades, and everybody misses the deadline, and the whole system comes crashing. With fixed priority scheduling, if you are running an overload and you're missing a deadline, you only miss deadlines of lower priority tasks first, and only in the end you miss a deadline of the higher priority tasks. The higher priority tasks are protected because they can preempt the lower priority tasks. And so that kind of protection is basically the really important thing that, safety critical, life critical systems care about, right? So here is an example of EDF under overload conditions, where we we have this task that is getting scheduled, and then it's so far it's fine. It's meeting its deadline. It's meeting its deadline. It's meeting its deadline. Meeting, and then it gets overloaded over here. And why did it get overloaded? Because maybe the task had some extra work to be done over here, and it had to finish that work, and so it missed its deadline over here. Normally it had 2 units of work, and in this case the task came in a little late, right? And then the task basically could not finish at that time. But because it couldn't finish, the next task missed its deadline, and because the next task still took up the time, and then the next task after that missed its deadline, and basically it caused a cascading effect that all the tasks start to miss their deadline over here, right? So how did it start? So far we were fine, everybody met their deadlines over here, and then the second round started, everybody was meeting its deadlines, and then the third time we come around, this task comes in a little too late. Because it came in too late, it was supposed to have started over here. This was supposed to have started over here, but it came in too late. And then because it came in too late, it started this cascading overload. In rate monotonic scheduling, if you have an overload and this task comes in late over here, it will miss its own deadline, but it'll get preempted again by higher priority tasks over here, and they don't miss their deadline. Only the lowest priority tasks miss their deadline over here. So the higher priority tasks are always protected in that sense, right? So, so that's basically the difference between fixed priority scheduling, rate monotonic scheduling as an example, and EDF, which is an example of dynamic priority scheduling over here. So any questions so far? Does that make sense? Okay. Don't look so excited. Oh, it's okay. Okay. Yeah. All right. Any other questions then?
I have a quick question. So if you were to do the RT test with the interrupt priority scheduling, is that still the same like procedure?
It's the same procedure. It's just that you would have the the interrupt with the deadline, as I showed you how with the period based on the period of the horizon you're looking at, right? So the period will go up to the 200, for example, but if you're looking at a horizon of just 100, then the period will be 100 for that task. And then it keeps going up. But it's exactly the same way. But you will basically always have to include the high priority interrupt as part of your calculation.
Okay, sounds good. Thank you.
Yeah. Okay, any other questions? So we are in the flipped classroom mode where you would watch the lectures beforehand and then come and ask questions here, because the lectures are already ready, right? I don't have to give them live. So all good. I'll stay on for 2 more minutes. If you have any more questions, then we can answer those. So the next lecture we will cover concurrency and race conditions, and that's probably one of the trickiest lectures, and that would normally be given in 2 sessions, so we can use 2 sessions for that, and you'll have a worksheet and a quiz that is dedicated to that too over there, and that's full of a lot of trick problems, and you just want to get a good idea of how to solve that. So you should watch the concurrency and race conditions lectures after this point. All right, no more questions. Everyone good? Give me a thumbs up if you're good. Okay, good. All right, great. Okay, guys, so then we'll stop here. And then if you have any questions, just send it to us on Piazza and I'll answer them in the next lecture. Okay, all right, thank you.
Thank you.